So let me first start with a question. How many of you have already tried the web support of Flutter that is provided? Oh, that's a lot of you guys. That's nice to see that you all tried it out. And how many of you already use an app in a production setup so that you're really running it live on the web? Okay, that's not so many people. So we'll see. Hopefully my insight that I share with you today will give you a better understanding how this will be possible and will it make it more attractive for you. So hey, my name is Joachim Böhmer. I'm a Flutter developer at Lotum, and we are a small game development studio in the center of Germany. Our games have quite a big outreach, and I'm also a talking head at the Programmierer podcast. We also talk about Flutter topics here and then. If there are some German attendees here, if you heard about it, then it's good. If you've not heard about it, then check it out. And on GitHub, on Flutter, and on Twitter, you will find me under my handle, Captain Koala. So, what I will present to you today is about a mobile game that we are working on, and it was first developed as a native Android and iOS app, and it's already quite old, so it was already published in 2012, and so we celebrated our 10th anniversary this year. And from the development setup that we had at this stage, it was quite common for the mobile apps that was developed at that time. So we had developed for the Android and iOS platform separately. We had Objective-C code for iOS, and we had Java code for Android, and we had a dedicated developer for each platform. So, and he was always developing for this platform alone, and we didn't expect the success that we had for all these years. So we still have about 1.3 million daily active users, and we have a very big fan base of users that are playing our game each day for years now. In 2017, we launched our game also on the Facebook Instant Game platform. And we already had access to this platform in the beta phase, so we were one of the first games available on the platform. And here on Facebook Instant Games, you can play HTML5 games on the Facebook and the Facebook Messenger. And it has to build with browser technologies. In 2020, we decided to rewrite our native app. The biggest problem was that we had the separated code base for Android and for iOS, and these code bases had dramatically diverged. So we had features on one platform that were not available on the other one. And also the design was not consistent for all this. The biggest disadvantage that came up with that was that the development of new features was really becoming slow. And it was also really hard to constantly develop new features on this shared code basis and test them iteratively with your users, what you want to achieve in the best run. So we decided to do a complete rewrite. And this complete rewrite we did in Flutter. And right from start, we had a very good developer experience with working with Flutter. Previously, we have already taken the attempt to implement the 4Pix game with web technologies and wrapping it in an HTML5 container, but we had to use many workarounds, and in the end, the app didn't look very native. For example, endless scrolling lists and pager widgets were really hard to tackle. So with the rewrite in Flutter, we instantly got a much better user experience. The users got an instant look and feel, consistent look and feel, and we were able to port a lot of the features that were previously only available on the native platform to the instant game as well. And the biggest benefit that we saw is that we had the whole team working on one shared code base. So this was best to avoid knowledge silos, so one developer could where only one developer knows the details of one platform, and also a completely different team spirit evolved. So we had more communication, more sharing of knowledge and about the features and the technical aspects, and we had also a shared responsibility for the code. And with that, we were able to achieve a much faster feature development cycle. So we really fell in love with Flutter at that time. So then we thought about, okay, in the middle of last year, it was that we also want to rewrite the 4Pix instant game. After the initial success that we had on the platform, we had a steady decline in the user base, and many of the features that we brought into the native app were not ported to the instant game afterwards. And we also didn't implement all the new APIs and functionality that was common into the platform. For example, there was a very interesting tournament features where users could play against their friends, some kind of match. And also, what was quite problematic, that as a software stack, which was written in Pixie.js, was not state of the art anymore. So it was really hard to maintain the system, and we wanted to get this to a shift. And let us first take a look at the requirements that are posed on the instant game platform. So probably not all the improvements that I will show today are also relevant for you, because you're maybe only developing for desktop browsers. But for the instant game platform, it is really crucial that the users are able to instantly play the game. So because all the other games are just one click away, so we don't have a really strong commitment of the users playing our games. So as one. And Facebook always stressed the fact that it's very important to have a very small bundle size. So the less data is transferred, that is transferred on the wire, the faster the game is ready to play. And faster startup times also leads to less churn of the users on the loading screen. And especially Facebook is used all over the world, especially in South America and in the Asian markets. We encounter many users that only possess a device with not so good resources. So we also need the ability to provide a good game experience also to those users. And we decided to do the rewrite in Flutter. And the main benefits that led us to the decision, because we thought about, okay, we do it also with web technologies, we have a good knowledge in our company about that we would be able to use the same shared code base for the multiple platforms. So in other projects, we had the situation as well where we had separate code bases, and like I said, it was really hard to maintain in the long run. So using the same code base would also reduce the mental load that is imposed on the developer, because he doesn't have to switch between different programming languages every time he switches to the other platform. And we expected that we would be able to develop features much faster for all the targeted platforms, because we could just port over the features that develop for one platform to the other one as well. One drawback that we saw from the beginning is that we were aware of that the Flutter web platform was very, very new, very, very young, and that there would be a good chance that we encounter a lot of obstacles while implementing the app. So let's see how this turned out for us. Flutter is rendering its contents on the web. So how does the web renderer work? Probably most of you know that Flutter has two options of rendering for the web. The first option is the HTML renderer. And the second one is the CanvasKit renderer. When you build the app with the web renderer auto flag, the HTML renderer is used for mobile browsers as soon as a mobile browser is detected, and the CanvasKit renderer is used for desktop browsers. And this is not ideal because you don't have a consistent look and feel between the different platforms, between the different browsers. And the CanvasKit renderer, the HTML renderer is probably using the mobile browser. The mobile browser is using the HTML renderer because it's probably every time that the resources of those devices are more restricted, they have less processing power, less network bandwidth. Whereas the CanvasKit renderer uses also WebAssembly besides HTML5 and JavaScript. And what was really crucial for us was the bundle size. So this was the first differentiation that we had to take. And both approaches need the Dart and Flutter runtime. And the Dart and Flutter runtime itself, when you just compile an empty project, you see that the generated main Dart.js file is about 1.3 megabytes. When you transfer this over the wire, it's only 380 kilobytes. So this is the number that we have to look at. But with the CanvasKit renderer, you also have this CanvasKit Skia engine. And this is a CanvasKit module. This is about 7.1 megabyte when it's on lying on your storage, but when you transfer it over the wire, it's about 2.9 megabytes. And this is quite huge for a normal web application. So let's have a look at the HTML renderer, because we thought, okay, because the bundle size is so crucial for us, we should first go with the HTML renderer and see how it works out, that we can provide all the design elements that we have with that one. So let's have a look how this works under the hood. For the HTML renderer, the whole document is seen as a drawings canvas, because this is how Flutter works. Flutter just communicates with a canvas API where it says, okay, draw that component on that position and give it some decoration. And the Flutter's canvas API is able to paint a lot of different things. So it's able to paint shapes, paint images, and paint text elements. And while Flutter does all the layout calculation, the HTML renderer creates absolutely positioned DOM elements that it just puts onto the HTML document for each element that is drawn. And what you can now see that depending on the complexity of the drawn component, that he creates for image elements just an image tag, and for the text elements he creates paragraph elements. But what you can also see for special elements like this, a rectangle with rounded corners, you have some custom web components that are maintained by the Flutter runtime under the hood. And you have quite a set of components that you can use there, or that the Flutter, the HTML renderer is using under the hood. But what you can also see when you look deeper into the DOM tree, that you can see that a lot of canvas elements are created. And this is special probably to our design, because we have a lot of gradients and other stuff, and shadows on the design. This is something that is quite common to the app. And therefore, yeah, we had to see, okay, with all those canvas elements, what can we do about it? And we had one requirement of our designers, and this was the main cause that we have to preserve the look and feel of the apps. So we were not able to reduce the decorations that are used on the native app side on the web part. For a normal web app, it's always possible to talk to your designers and say, okay, this is not good to make it with CSS. The decorations are becoming too complex to be smoothly rendered on the browsers. So there were no the possibility for us to really reduce the complexity of the decorations that we had. And as soon as the decorations get too complex, the HTML renderer cannot represent them as CSS styles alone. For example, the case when you have a gradient painted on the surface or some kind of box shadows, that means that always Flutter needs to create a shader for that. Then the HTML renderer is not able to present that as a canvas, as a normal HTML element, and will create a canvas element out of it. But as you probably know, a lot of canvas elements on the surface always brings in some performance impacts. So as soon as you have more than maybe 20 elements, and this was normally the case with our designs, you will definitely see that it's not running smoothly when you're doing it, or when they are located, contained in animations, or if they are put on endless scrolling lists and pager components. So one thing that we first thought about was, okay, how can we reduce the amounts of canvas elements that are created? And we tried to apply a technique that we also already used heavily in previous web games that we developed, and this is to replace the complex decorations with 9 slice images. For 9 slice, the image is divided in 9 sections. So you have the normal image that is split like this. And when the elements are scaling, only the corner elements are kept they are unchanged, and the center and the vertical and horizontal elements are stretched to the size that is needed. What was causing this, or what led to the situation that we now didn't have those many canvas elements, but we had a lot of different image elements that were created on the canvas. So what we decided was to reduce the 9 slice images and create some kind of 3-slice images. Therefore, we implemented an own decoration image class that could eliminate the corresponding slices when the center or the bounds of the center slice property of the decoration image were 0. And with that, we could dramatically reduce the amount of div elements created on the DOM. And what we implemented is that we did some kind of render path switching in the basic widgets of our apps. So whenever we run the app on in the native app on Android or iOS, we just used the normal decoration images. As soon as we rendered the app in the web browsers, we replaced all those decoration images with the corresponding 9-slice images. And this concept prototype that we created with that was really promising. So we had some good performance situations. But after developing on this approach about 3 or 4 weeks, we saw, okay, we ran into a lot of unsolved problems that we were really not able to tackle. At first, the developer had to handle a much higher complexity because we always had to ensure that the rendering paths for both platforms are looking properly, so that the configuration definitions that we did and the corresponding center slice and 9-slice images were looking the same. And the designers also had always to create and export the corresponding sliceable images. And whenever we implemented new components, it often happened that we created new canvas elements on the DOM because you didn't really know when a decoration was becoming too complex that it would be rendered as a canvas element. And therefore, we always had to inspect the DOM tree after we had built a bigger feature to see if anything had changed and if I have to bring down the complexity of the app again. And even though we reduced all these known slices to 3 slices, we still saw a significant performance impact. So as soon as you have too many images as well on low-end devices, the animation will get janky. And even on currently popular Android devices, we saw jerky animations and a bad performance that we were not able to roll out to users like that. So at some point, we had to pull the trigger and realized that the HTML render approach was not really to a satisfying result for us. To allow, we were able to just put the switch on and switch the web renderer and using the CanvasKit renderer as a basis. And let's see how this turned out for us. At first, it's maybe good to get a better understanding how the CanvasKit engine works under the hood. So CanvasKit is a port of the Skier engine to WebAssembly. And when we look at the files that are generated in the build folder, you can see that we have a CanvasKit WASM file. This contains the ported Skier engine. And you can find also a CanvasKit.js file. This is just the JavaScript bindings for the Skier engines that you can call the corresponding drawing operations from the JavaScript part. On top, you will also find a main.js file, and this will include your app code and also the Flutter and the Dart runtime. On startup, the Flutter web engine will put a single canvas element into the DOM, and we'll hand down the image buffer of this canvas element down to WebAssembly, because this is the only possibility how WebAssembly can communicate with elements on the DOM. And this will be wrapped in a SK surface instance, and then the CanvasKit engine can directly paint the pixels on that surface, which leads to the corresponding pixels get painted on the canvas element that is located in the DOM. So now Flutter is responsible for doing all the runtime layouts and do all the calculations to get it right. And then Skier is responsible to paint the corresponding pixels on the SK surface and really draw the interface like it's intended to be. But as well here, when switching from the HTML renderer to the CanvasKit renderer, we saw that for most devices that we had a very good performance on current devices. So it was almost comparable to native. And also for all the devices that we had in the test pool that are a little bit older, as well on those devices, we had a very good performance. And the best part for us was that we could use the same decorations that we used for the native app. But when we tested the CanvasKit render on really low-end devices that we also see, for example, especially on the Asian markets, we saw, okay, there the performance was not that good anymore. And because we said, okay, we also want to provide a playable interface for that users as well, we somehow have to reduce the details for low-end devices. And here you can see the interface just switched. So we just threw out all the, not all the decorations, all the gradients, and all the box shadows, and still the interface quite resembles the interface that we had before. So for the user, it's more a flat design that's maybe also a little bit more modern, but it's for him the same playable app that he can use. So it's not a big impact. And here we also just said, okay, some more complex animations, we will try to skip that and really to really make it feasible and playable for the users on those markers. And what we did here is just the same approach that we use for the HTML renderer, that we said we introduce 2 different rendering paths only in the basic widgets. So they are mainly located in maybe 12 or 13 different positions in the app. And this resembles that the whole UI is changed to the different rendering paths. And we heavily reduced the level of details here. And in this case, we still have that playable version. We now have the situation, and this was one problem that we faced, that we were not able to load the CanvasKit runtime because normally it's hosted on unpackaged.com. And this was, for example, blocked by the content security policy of Facebook. And luckily, you have the ability to host the runtime in any location that you want. And for that, you can use the Flutter Web CanvasKit URL Dart-defined that you can hand over to your build command. And then you're able to change it to whatever you want. And you can also say you put it on your own CDN as well. One drawback is that every time a new Flutter version comes out, it can be that Flutter references a new version of the CanvasKit runtime, and you have to check if you're building the app without that flag, what is the version that is created by the new Flutter version, and then change your hosted version of your runtime to the corresponding version. So normally, the CanvasKit runtime is first loaded after the main.js file is loaded and executed. And this is also something that takes some time. So, for example, for a normal app, you see around a bundle size of 600 kilobytes. So you always have to wait that time, and the browser could do more stuff in between. And how you can improve the loading times of the CanvasKit runtime, that you just say, or you preload the corresponding runtime by using link elements in the page header. And this will start loading the CanvasKit runtime as soon as your page loads, and it will be ready if your main.js file is also available. But when you're now running with CanvasKit, and we discovered that in our crash reporting tools, that our app was not starting because WASM is not supported or blocked. And for our game, for instance, it was about that 3% of our users weren't able to access the game because WASM was blocked. And that could either be that the user deactivated WASM in the browser settings for himself, or, and this is the more likely case, that some kind of installed ad blocker is preventing the access to WASM. And for all those users, yeah, it's not possible to really enter your app if you're only providing the CanvasKit renderer version of that. And we tackled the problem that we fall back to the HTML renderer when we are checking that WASM is not supported. And we do that before initializing the app in Flutter on the JS side. And if we detect that WASM is not supported, we make that fallback. And then we just set the corresponding Flutter web renderer property to HTML. And in this case, the UI is completely rendered with low details. So we are falling back to the low detail mode that we have that we implemented also for the low-end devices. Now the user can, even though he doesn't have that WASM support enabled, he can play the app in the low detail version, but he still has a version of the app that is playable. One other technique that we had to implement to really achieve near-native performance was the preloading of assets, because with the CanvasKit renderer, we definitely saw that we were having lagging assets when we start the app. So what you can see now in the videos is playing here, that the apps, or the first image, it just spans up the corresponding layout of the UI because it is loaded a little bit faster, and everything is coming a little bit later into the screen that it's supposed to be. On native, it's not a big problem because you have the corresponding, the transport channel, the fetch mechanism via message channel is really, really fast, so you can just instantiate your images directly on your widgets, and the transport mechanism will be so fast that you don't really see that it's a problem. But here on the web, all images have been loaded over the network. It always takes some time until they reach your browser. And you definitely can introduce some kind of loading spinners in all your app, but this would definitely make the app feel native again. So what we introduced here was some kind of, and the effect was less striking in the HTML renderer than it was in the CanvasKit renderer, because here all the corresponding techniques of the browser are used to really do the loading of the images and other resources. And what we implemented is some kind of preloader mechanism. And those preloaders are located directly at the pages, because the page knows best which assets are used by itself, and all the widgets that it is incorporating or that is building inside of its build method. And we also provided the possibility of handover routing parameters, because sometimes you have contextual resources that are only loaded if you enter a special route with a certain parameter. And then you have a central loader registry where you can match your routes with the corresponding page loader elements. And whenever the corresponding page is loaded, then we preload the corresponding subpages. So, for example, when we go to the home page and we know the possible routes that I can access from the home page are, for example, the core game or some kind of the daily mode of the game, then we preload all the assets for those two entry points as well as the home page. So we're always sure when we enter the corresponding page, all the assets are already preloaded, and we just have the behavior that we have on the native app as well, without having any additional spinners. One nice package that you can use to maintain your assets more easily is Flutter.gen. And Flutter.gen operates on the build runner phase, and it scans your asset folders and creates for supported file types like images, sounds, and so on. And it creates an asset registry that you can access in code. In this way, you always have codable asset resources that you can reference, for example, in your widgets and also in the preloaders. And this was the good part, that we could easily keep them in sync. And also the good benefit of this library is that it heavily improves maintenance, because whenever you delete an asset, you will get a compile time error, and you also have autocompletion while writing your code, and you don't have to fix always or to look up the corresponding passes for the assets that you're including. Unfortunately, we also had to cope with another problem when using the CanvasKit renderer, and this is animation jank. Animation jank was out there for quite some time. Now we have the impeller engine that heavily brings down the impact on the iOS devices, but with the web platform, we still have that problem. And with animation jank, it's like when you run the animations for the first time, they will be jerky. And for the big games, this was especially noticeable when we did page transitions, because a lot of elements are moved around and pushed over each other. And what will happen every time the animation is run again, the jank will get lower and the animation will improve. So that it seems like even on Flutter Web, Skier can only execute fluent animations when it had access to the SKSL shaders. So these are created on the first execution animation and improved on all following animations. But because the generation of the SKSL shaders are so heavy, you will definitely have a lot of junk going on when the shader generation is happening on Flutter Web in the background. And most of you know this was a very known problem for the iOS platform, which has been solved now with the impeller engine. And what we did all the time there was always pre-building shaders with integration tests, bundling with your app to have that pre-warmed shaders already available when running the app on the device. So this possibility is not available for Flutter Web as in the moment. So what we do right now is that we do some kind of transition warm-up. So we warm up the transitions on startup while the app user is still behind the loading spinner. And we also push a route with a reduced duration. So what we realize is it doesn't really have to be the exact duration that we have for our page transitions later on. We can also reduce the default page transition duration from 400 milliseconds to 10 milliseconds, and it will have the same effect that the shaders are warmed up, and we have a very fluent animation afterwards. And we do that for all routes accessible from the main entry point. And one additional approach that we had to take is that we also run all the transitions for the main routes behind the homepage. So we just have a stack where all the corresponding widgets are put behind the homepage widget, and those are also run with those animations. And we had to implement both strategies to really have the best performance in iOS and Android devices. So only one strategy was good for one platform, but both strategies were good to have the best performance for both devices as well. So with this approach, we really had a much better first-time user experience, and we had the situation that both warm-up strategies were necessary, and the effect was much bigger on Android devices. So for iOS, it was already good that we just ran the app without the corresponding improvements. And now you can see an updated version of the app with where the caches have been updated behind the loading spinner, and you can see now the animations are running smoothly as you would expect them to run on the native app as well. So what future optimizations could be helpful in this area? So one thing would be to have a support for the warm-up RP and for the web platform as well. This is something that the Flutter team said, okay, it's probably quite doable and not so complex to implement. And then we will call the shader warm-up on startup and probably don't need any page transition operation then in the background. We could also think about rebuilding the shaders on integration tags and bundle them with the app. This is another option that might even come up, but the best option would be, and this is something that is not on the roadmap of the Flutter team right now, that the impeller engine will somehow be ported to the web platform as well in the future. Because what we can see from iOS, it's really a game changer in that area, and it would be good to have that ability in the web platform as well. So some more improvements that we did to really make our app smoothly. And one first thing that we did is that we did some performance analysis because we saw that some devices, especially low-end devices, have a very poor performance at the beginning. And for that, we first implemented some kind of GPU model detection. We need that later on because we want to have an analysis which GPU model, which device model has which performance on the corresponding animations or transitions. With this information, we can do some device model classification. For Android, it's sufficient just to use the user agent string because Android is it gives quite a lot of information about internals. And but for iOS, you only got the information, okay, you're running on some kind of iOS device. You don't know which iOS device it is. And therefore, you need this GPU model detection because here, you can say, sorry about that, you use the information about the screen ratio, about the pixel density to identify, okay, and also the GPU model to identify which iOS model are you really running on. What we also did is some kind of graphics performance tracking. You can use the API of scheduler bindings to add some timer callbacks, and this will give you a lot of time frames that you can use to analyze, okay, how is the FPS rate when I run an animation or if I do a transition, and this you can use to log all those information to your backend logging system and build those clusters, and in the end have some kind of switching of rendering mode. So this is something that is generated programmatically for us. we have a list of corresponding devices where we have identified during this performance analysis that we have a bad performance. And whenever we detect that the app is launched with a device that falls into that cluster, we just switch to the low detail mode and let the user interact with the game in a version that is much more capable of handle the resources that it has on the device. What we also did to improve the playability of the app is offline support. And for offline support, you can use the service worker. And the problem is that the default service worker of Flutter Web is really limited in the way it handles the resources. It can handle very good the resources that you have in your own bundle. Therefore, it's pre-configured. It will scan all the resources that are contained in your builder folder and will create a so-called resource manifest so that you can check whenever time it starts which resource that it has to prune, it has to delete, which has changed because it tracks the revisions or the file contents of those files. So what you can now do to really, because normally you would also have the situation that you also load resources from external locations and that you would like to implement a custom worker. And for that, there's a good tool from Google, it's called Workbox. And you can implement a custom worker with Workbox on the client side, where you just say, okay, it has a lot of special functionality where you can say you just register a route. You don't have to care about the deep level of how you interact with caches and like that. You just tell them, okay, whenever you encounter a route that comes from a certain origin or that comes for a certain URL, you put it in a certain cache and you can define different caching strategies, how Workbox will interact with those resources. And what you can now do, what the Flutter package or the Flutter build process does from itself, that you inject the corresponding manifest with Workbox build. So this will do the same. It just scans your output or your build folder for the corresponding resources and injects the corresponding manifest in a certain tag in your Workbox file, so that all this functionality that the Flutter, the default service worker provides, is also available for this setup as well. And you can also do a lot of other stuff with your custom service worker. For example, you can implement prefetching of resources that are needed in some time. For example, we preload the images for the 50 next puzzles in the background of the user, so that whenever he goes offline, he has at least 50 levels to play and continue the game with. So let me take a resume about our findings. So what we had and what we really disliked is that we had a high initial invest that we had to take to really make the Flutter web platform for our use case really feasible and have it a very similar performance to the native platform as well. And the investment is still ongoing. Like I said, all this device cluster performance analysis, we are still constantly improving it to really bring the best performance to all of our users. And the web support at the moment is not quite optimal. It's steadily improving. So, example, we had to fork a lot of Flutter packages in the beginning because the functionality that was needed for us was not present. But it's continuously improving. So we have already switched back to a lot of the corresponding official versions of the Flutter packages. And we still see a performance gap to native. It's quite close now with all the improvement that we did, but probably Flutter Web will never have the same improvement that you could achieve with HTML and CSS alone. Maybe it's possible with the Impelled engine. I hope for that, but we will see how this ever will happen. And we still have some visual glitches on some devices, for example, Razer phones and some Huawei devices. They have some fragments that we can really not tackle. And for example, that some text elements are not drawn correctly. But what we really liked about this approach is that we now have a large common code base that everybody is working on. And whenever we develop a feature on one platform, for example, the Instinct platform is very good for developing features because you just have a deployment process that is instantly, you roll out new versions, all the users see it, you can iteratively change your features, and when this feature is successful, you can bring it over to a platform which has a longer development cycle or deployment cycle like the native platform as well. And this gives us the ability to go to much other new platforms that are arising in the HTML5 gaming sector. And we can use the same code base as I mentioned earlier. And what it's led to in the end, that we really brought back the joy into development, because you're now developing on one code base. It's really good to talk with everybody in the team about the features that you're developing. You don't have that split anymore. And I think this weights out all the other drawbacks that I explained before, to really have that team consolidated and working on the same stuff. So, yeah, we still love it. And thanks a lot for your attention.